Okay, so this is, I think, if I understand correctly, the last talk of the day. This is about combined characterization of control, and it has the challenge that I am, supposed to give a review or school talk, which you typically um, give about a topic that you have worked on for decades and have well reflected in many papers. Here, our preprint is probably coming out tomorrow. So this is work from our group at Saarland University. Federico has actually by now moved to our host at IBM Rüschlikon, and we also have a volunteer called Anurag. So some of this will be a bit of a repeat relative to the presentation in Padua, but specifically in the end of the day, people sometimes like repeats. So I remind you why applying optimal control to superconducting qubits is actually difficult and what we can learn from the cases where it worked. And then I will show you that a really important part is to close the loop and to combine calibration and control in a very close way. I'll show you the idea and an example and a few observations and outlook. So let me start kind of by looking at a number of extremely celebrated experiments in superconducting qubits that came out over the last year. On top, you see the Google quantum supremacy experiment, which next to all the PR it got, had the remarkable property that that you see on the right, that you had errors in an appropriate measure. This is a measure that can be computed that is related to fidelity, that were typically quite consistent along those steep lines around about 1% and a bit below. Now that is already pretty good for the field of superconducting qubits, but for really doing something useful for quantum computers or even doing fault tolerance, that is not enough. In fact, the way how Google has benchmarked that they have reached this quantum supremacy was very cleverly designed, so you could detect this even in the presence of high level of noise. Now, IBM also has a chip of the similar size, and their favorite measure for benchmarking is quantum volume, where they essentially try to run a square algorithm. So an algorithm that has a circuit depth or a number of hard gates that is as large as the number of qubits. And their record, as reported last month, is a 6x6 circuit. So these are 6 qubits that are sitting in a much larger device. And if you think that my best benchmark for a measure that includes fidelity is reached on a 6-qubit chip, you may wonder, why do I need devices with 50 or more qubits or even 65? And you see below on the lower right that fidelities have improved. The gate error histogram becomes lower and moves to the left, but it's still not where it's supposed to be. So currently, as much as the PR on superconducting qubits talks about qubit numbers, it's really fidelity and error that's holding us up. Another remark on the left, you see the qubit layout in IBM's device, which is following what IBM calls a heavy hexagon architecture. So you see that this is a 2D architecture, but the connectivity is very low. This has to do with frequency collisions, and I'll mention how control theory can help that as well. So this means we want to do good gates, and gate design, of course, involves numerical optimal control, which you have heard about already quite a bit. So we want to take a chip that somebody has made. I'm still using a relatively old picture from Google on the left, because you see everything. It's not in a plastic box, where you have human-made components that need to be characterized, and you use some control box to make the elements of the algorithm. So we want to make gates that have high fidelity, that are so fast that any unstructured decoherence can be beaten. And of course, with structured decoherence, you can play with the speed, and that it actually works under realistic conditions. And what I call other fields optimal control is actually roughly what you learn in most talks during the QuSCo schools. Namely, let's just look at GRAPE in its kind of original form, which is that we want to generate all possible gates on n qubits. So we want to do single qubit rotations and make an entangler and figure out how to make them. And we like to use systematic mathematics. So we take our Hamiltonian, we split it into drift and control fields and controls. If we are careful, we are checking for controllability by computing the Lie closure. We can also just try or just know it already. And then we can, for example, use grape by designing the time evolution. I'm missing an integral in the formula on the left, and adjust the amplitudes that you're programming into your pulse generator to get us as close as possible. And the result may be something like that on the right. This is actually from the PhD thesis of Daniel Egger. It even includes a sample number. And the whole point of this plot is to show you that what comes out is fairly complicated. A lot of you have probably done optimal control themselves and have seen even more complicated things. But now you can see that we're also showing some parameters of the system in there. And we may wonder, what happens if these parameters are a bit uncertain? What do we have to do to the pulse? How do we debug this? And in fact, already 6 years ago, we realized how hard this is. And we did with what is now the Google group, which was back then the Santa Barbara group, we did a measurement of a pulse like this applied to a qubit setup. And we could actually beautifully see that theory and experiment, which you see experiment on the left, and on the right, you see a title page with theory, of the error landscape or the control landscape look very similar. The axes are disappointing because in the best case, you get a 70% success probability on the left. So, you know, we understand the error, but we cannot really fix it. So why is that? Well, this is because the Hamiltonian that I have shown you is certainly incomplete. In a human-made chip, there are lots of degrees of freedom called junk. There are also uncertainties, which you can also actually write as junk. They can appear in the system and in the control, and I'll show you a few examples later. So we don't quite know what the model is and whether it really gives us a good enough description of our system. Also, what we are sending from our arbitrary waveform generator to the chip sees the propagation uncertainties, which are sketched in the red circle on the right, where you see that a small uncertainty can move your levels. So what you're putting into your Hamiltonian is uncertain, but also you're sending this to a big setup of filters. So what you're sending to your sample may be wrong, and you need to pre-distort what you're sending so it arrives in the sample in the correct shape. And in the case we've looked at a couple of years ago, you see, like in panel C, that we do get the benefit of gradient-based optimal control, that at the optimum point, at the blue spot in the middle, we do have a maximum. So the gradients are flat, and we can function is flat, the gradients are zero. So we can, in fact, tolerate a bit of noise. However, if we blow this figure up, which is shown on the left in panel B, this peak is so small that you don't even see it. It looks like a red cusp. So this intrinsic robustness here doesn't really help us. So there's fabrication uncertainty, there's transfer function uncertainty. And to characterize this is all very sample specific. We really need to use the qubit and the chip itself to characterize what's going on. Now, I should point out that there is a solution in the field of superconducting qubits where people do apply numerical optimal control results routinely, and it is mostly done at the Yale group, and the pioneering work is by Jerez. And this is done in the setup shown on the lower left. This is a so-called three-dimensional transmon, which is an unusually clean system. And in the middle, you see some pulse shapes that they were implementing successfully. And you see that they're fairly complicated. The other thing you see is that the x-axis, the time axis, goes up to 500 nanoseconds, which is very far away from the quantum speed limit. Now, let's think about Fourier analysis. The quantum being at short times means that you need to understand your system over a large frequency bandwidth. So if you go for a relatively long time, if you're not exploring the speed limit, you only need a model of your system over narrow bandwidth. And this, in this very clean system, is in fact feasible. But now we want to use the potential of optimal control and also make a really fast gate. Now, a very nasty example of degrees of freedom that you can have are two-level systems. I'm showing you mostly these plots on the left to scare you that the origin of these two-level systems involves some messy material science. So on the left in panel C, you see blue qubit electrode, but on top of this you have an oxide which is disordered, it's glassy, so it has little small dangling bonds like these brown points. I somehow don't have a mouse pointer, but you see these brown circles that are moving around. These are slowly moving systems that are sloshing between two configurations. You also see oxygen adsorbate, so you see some chemical junk on top that makes flux noise and other stuff. And these are quite kind of well characterized. They have to do with the fabrication process, and it's not easy to get rid of them by making better samples. Moreover, it actually turns out that intrinsically they are quite clean. On the right, you see a spectroscopy result of where the black line would be the qubit alone, but you see interruptions that correspond to an avoided crossing. And this avoided crossing basically indicates that our qubit is interacting with a very coherent quantum system, which is one of these two-level systems. And people have actually shown that you can even turn them into qubits. However, this is not scalable because these are truly random. And we already see that in NV centers, it is pretty difficult, but by now feasible, to make impurities on demand. But in these systems, within a junction oxide, making impurities demand is a no-starter. So we have to deal with some degrees of freedom. We don't know the number. It depends on fabrication. And they are very coherent, so they make a very non-Markovian noise source. So here is a known example from our group where optimal control in superconducting qubits has worked. Last year, we have published a review article, and this is drag. And this has to do with the remarkable observation that superconducting qubits, as they have been researched, became bigger and they became less anharmonic. This is just a curiosity many people are not fully aware of. So the system on the top left, you see, has a 1 micrometer scale bar, and the structures are all below 1 micron. And this is from a 1999 experiment from Yasu Nakamura. So this plot is more than 20 years old. On the upper right, you see a transitional qubit design, the quantronium from our friends from the quantronics group. And on the lower right, you see the modern transmon. And you also see a scale bar. So the arrow on the bottom is a bit hard to see. It's 200 micrometers. So this is a lot bigger. And this is the more modern thing, which is kind of nanotechnology in reverse. In the middle, you see the energy landscape. Black is the zero state, red is the excited state, and the x-axis is charge noise. And the upper lower panel refers to the Nakamura qubit. And you see there the splitting from blue to red is very different from the splitting to red to blue. So this is highly anharmonic. The modern transmon, these splittings are almost the same. So this is not very anharmonic. And we have a long time ago, more than 10 years ago, developed a technique that shows how to deal with this. So the problem is that if I'm now driving my working transition, omega 01, shown on the left, and I do this very fast, which I would like to do, then automatically the Fourier spectrum has some overlap with the leakage transition, and it drives the transition that I don't want, shown on the lower left, and I'm getting errors. And you see on the right, these are error measures as a function of gate duration. And you see that at short times, there's an upturn when the time gets shorter and shorter. And this is because you essentially now exploring that your qubit is almost harmonic. And we have come up over the years with a whole bunch of techniques called drag and WAHWAH that are based on relatively simple pulse shapes that allow you to mitigate this. And they have, in fact, been tested in experiment. Drag, for example, shown on the upper left, simply assumes that your pulse has a carrier envelope shape. So you have a cosine omega t and a sine omega t. And the envelope of sine omega t is the time derivative of the envelope of cosine omega t. WAHWAH, shown in the middle, shows that omega x, which is a similar object, also has a very simple structure, and omega y basically has the same differential equation as drag. So these are pulses that are enormously simple, And basically, experimentalists could simply take the software that they use to model their experiment, fiddle with these Ansätze a little bit, and get it going. And fiddling with Ansätze is, of course, kind of very primitive optimal control if you want to do better. So this was their workflow. We have found for them things like drag and WAHWAH. They were simple. They put it on the experimental toolkit, and they did an experiment. And again, I've shown you that for the reasons with characterization, this is typically not done with complicated pulses because the calibration on the experimental toolkit, if your pulse has a couple of hundred parameters, is not possible. In fact, here is a slide that from Google you famously can only get by taking photographs, how Google calibrates their processor. What do you see here? First of all, you see a graph that is very, very complicated. So this is the quantum supremacy version of this workflow. And secondly, so you can ask, why is it so complicated? Well, because it takes the recipes that have been developed in the lab over 20 years of experience, and it's programming them in a systematic way. And as the ex-Google chief scientist, chief hardware scientist, John Martinez liked to indicate, 1 or 2 points in this diagram typically correspond to 1 PhD. So this, on the one hand, to make this work as a calibration is very impressive. On the other hand, it seems like with the tools of optimal control, we should do better, even though I've now motivated why people are doing this, because they have these difficulties with sample characterization. So what we proposed also a few years ago, sorry, there's a lot of history in here, is that one really should now do 2 things in a row. One is you do the typical open loop optimal control with GRAPE or other algorithms based on a system that you have designed and characterized. And then you should do calibration. So you should measure the fidelity on your experiment and update pulses in closed form. For this, you need good benchmarking of whether your result has actually worked. And you need simple pulses because you cannot handle too many parameters. For good benchmarking, for all of you who have participated in the school in Saarbrücken, I can remind you that I've explained randomized benchmarking to you, and you are the target audience. So let's be very brief. You're essentially, for randomized benchmarking, running a long gate sequence that is random in the right way, and then you undo it, and then you measure the survival probability of the state. We have slightly modernized it that you don't even have to undo it. You're basically now not looking at the survival probability, but at the switch probability, by which you can rerun the sequence without initializing. And embedding this into pulse calibration gives you these plots on the right, where you nicely see trajectories, these gray dots in this blue and green landscape that jump into the optimum of the control landscape. And you also see that this is a 2-dimensional control landscape. So this is fairly simple, but this closed loop scheme that I've shown in the last slide in these simple cases really works. Now, before going to our new stuff, let me give you a technical intermezzo. And this is based on popular demand from the Padua school, namely for building the machinery we have benchmarked optimizers. Many of you have seen that nailed or meet, this is simplex technique, that is also used in the upper right, is kind of the workhorse of this type of online optimization, but we wanted to see whether we can get better. So we went through this is work of Kevin Puck mostly, we went through a rather exhaustive list that we essentially pulled off various known sources and checked how we can make them work for quantum optimal control. Here is basically a phone book of them, and I'll focus on some benchmarking results later. And we first benchmarked them on analytic goal functions that are very typical for this literature. So on the upper left, you have the sphere, which is fairly benign because it has 1 minimum, and you can enter the minimum at the same speed from various directions. The slightly harder one you see in the middle is Rosenbrock, where you have a 1 minimum that is on the x equals 0, so on the y-axis of the dark blue line. But you see that when you are there and you move parallel to the y-axis, that this is very steep on one side and flat on the other. So, but there you can expect to go quickly but overshoot. But it's very flat around the blue ridge. So there you are very slow. So here you're testing for optimizers that can handle very asymmetric landscapes. And on the upper right, Rastrigen is essentially extremely nasty because it has a lot of local extrema. It looks like corrugated cardboard or an egg carton that is slightly kind of bent up like a taco shell. And one of these many local minima is the global one. So we looked a little bit what seems suitable and also in handling noise, and we chose Powell's method, 1+1 evolution strategy, and CMAES. Those are all available in libraries, and we tested them around our beloved Nelder-Mead. This is what we got on the test problems. So for sphere, most of these more advanced optimizers do really well. Powell jumps around at very kind of along the minimum, but otherwise they drop fast. Nelder-Mead is rather slow. For Rosenbrock, the slightly more nasty one, CMA is doing really well. And for Rastrigen, generally the Fidelity convergence is also much worse, but also CMA is doing rather well. If we now instead put this on a quantum control problem, so to take randomized benchmarking results for a drag pulse, we see a similar picture. Nelder-Mead is converging, but rather slowly, and 1+1, but also CMA are converging much more quickly. So we recommend trying out CMA. You know, we haven't collected all the data in the world, but we recommend trying out CMA also for your quantum optimal control problem. Now, we should keep in mind that this is basically a never-ending story, and that there are various online resources in contemporary computer science. One of them is NeverGrad, which I think for graduate students is probably a very unpopular name of a package. And it's coming from Facebook research. You know, Facebook has to do a societal good somewhere, but also other projects which one can dig into, and we found this quite useful. But in general, we recommend CMAES. Now, the last ingredient we need for making C3 is finding a platform to find simple pulses fast. And as an appetizer, let me show you pulses that we have constructed for making a 2-qubit gate with a Flux tunable coupler. And all I'm showing you here is that these pulses have a very fine temporal solution. So if you want to draw this on time axis, you need thousands of points. However, drawing this on a time axis is a very inefficient way of representing it. You should rather represent these oscillating signals by Fourier components. And of course, you have learned in the first school that there is the Krabbe and method and its various more sophisticated variations that is ideally suited for programming, for optimizing objects like this. So why do we have GOAT? Why do we have something new? Is that we actually want to do something more because we are using this as a workhorse. We would like to see whether we can do gradients. So let me remind you of the setting. We again have a Hamiltonian shown on top with Hedged drift and controls. And now the controls depend on some parameters, but they are not given as a piecewise constant, but as a more efficient parametrization, such as, for example, sine and cosine with gentle envelopes. Now, what we would like to do is we would like to compute the gradient of this Hamiltonian that we can always do. We can compute the derivative of CK. This is an offline problem. And then what we do is we realize that we can write down a Schrödinger equation for the unitary matrix and its gradient. I'll jump forward and then come back. The reason why we can do this is that we can essentially exchange the order of derivatives. Instead of computing d alpha dtu, we calculate the derivative of h. So by solving this pseudo-Schrödinger equation, which unfortunately has a non-Hermitian and quite larger Hamiltonian matrix, we can compute gradients of the unitary and from this gradients of our cost function by co-propagation, by actually never propagating a gradient. And we like this a lot because gradients, whenever we have them for closed loop optimization, give us fast convergence. And this we like to use in the closed loop plot. Now we have shown for cross-resonance gates that we can reach some speed limits, but what we're mostly proud of is that we have been able to take the WAHWAH problem, so the problem of working with transmons that have essentially a frequency collision, where neighboring frequencies in the transmon are very close to each other, that those can be fixed. So we can, in principle, for identical qubits that are sitting next to each other, make a C0 with a fidelity of 99.2%, with a pulse shape that has a very fast oscillation, which here goes through this closed blue shape, and then a slow envelope. And the reason why I'm showing this to you is that this is in principle a mitigation for the problem that IBM needed to solve by this heavy hexagon architecture on the lower left that I've mentioned before. This is an architecture that puts qubits on a 2D lattice, but that is not very well connected. So qubits have, some of them have 3 and most of them have 2 nearest neighbors for precisely avoiding these frequency collisions. And because the qubits have fixed frequencies, those can also not be mitigated in hardware. And we can, in principle, use optimal control to fix them if we can really make it work. So this was all historical motivation and a lesson that I have not rehearsed the order of my slides properly. Now let's put all of these together in what is actually the title of the presentation, which is Combined Characterization and Control. I think I'm doing fairly well in time, so this will take another 15, 20 minutes. And somebody should protest if that's not okay. So let's completely get back to the drawing board. So I have now shown you that the models for superconducting qubits are not as precise as we want them to be for applying quantum optimal control out of the box, unless we do something special, like a very simple pulse or like a very long pulse. I've also shown you that by closing the loop, we can in principle calibrate. We can in principle readjust the pulse so it works. But this closed loop part teaches us nothing about the model. You're basically taking the simulation, replace it by the experiment, and then it works. And this is already progress. And this has not even been fully explored everywhere in quantum physics yet. But it would be much better if we can also learn the model, if we do that. And there's a whole theme in QuSCo of identifying complicated dynamics using optimal control. So we would like to learn something about the model for multiple reasons. A, we would really then like to have a model to understand where does the error come from. In fact, Max Werninghaus will tell you tomorrow about an optimal control experiment where the reason for the limitations that we explored were totally unexpected, and they actually had to do with running too much power over a control line, which one would have never guessed. So having this model really teaches us something about the experiment and allows us to characterize our quantum processor to make global process. But there's also a much more practical point, which is that the calibration of a freshly made chip will take a long time. However, the day-to-day tune-up, when something in the model drifts, when something in the chip drifts, so it changes its number from one day to another, that can be a lot shorter, but we want to understand as much as possible where this is coming from. So we want to like a good model. So a good model is a model that predicts what we can analyze and what we want with high enough accuracy, which ultimately means that we can make predictions with 4 nines after the comma. And for a human-made object, having such a good model is a very steep task. In fact, for PhD students in our group, A goal of his PhD is to find a model with this precision for a superconducting chip, or alternatively fail in an interesting way. And if we have such a model, we can do much better optimal control. So how would we do this? Well, here on the right, you see what we anticipate to be the workflow of C3, compliant calibration of control. If the C is an upper index, it means the whole package. If it's a lower index, it means the 3 steps. So you see this workflow has a simulation and an experiment component. We start with a model that is kind of okay, that allows us to run some gates and to run some rudimentary optimized benchmarking that should sit at 80 or maybe 90% fidelity. And then we use quantum optimal control, for which we essentially take our GOAT algorithm, that is the whole point why I've shown it to you, we implement it in a tool called TensorFlow, and we come up with good pulses controlled by some parameters alpha for a whole gate set. Because remember, randomized benchmarking needs a whole gate set, typically the Clifford group. Then we do calibration. So we do the closed loop calibration that I've also shown you before with restless Tuneup to essentially improve the parameters of the gate set. And the result of this data set, we write into a database that essentially tells us how did the performance change when I fiddled something at my pulses. And then I'm taking this data set, at the end of the day, after doing the first generation, I'm throwing it into a machine learning algorithm that essentially now does the following. It uses these conditional probability F2 that you see in the green box of C sub 3. So this is the probability of finding model parameters beta given experimental data cursive D. And this is based on Bayesian inference, which tells you if I can predict data, then from model parameters, I can also turn this around and predict model parameters from experimental data and show you a bit more explicitly how to do this in one of the next slides. And from this machine learning-based technique, we can improve the model and do new optimal control. So this involves some machine learning thinking, but this is a technique. These are techniques that are now becoming so ubiquitous that they're actually feasible to use with an acceptable learning curve. So this loop, we go around typically over multiple days, and if everything goes well, then the iterations become shorter and shorter because the C3 part will make the C1 part much more precise, and there will be much fewer surprises in the C2 part and vice versa. And of course, the ultimate goal is to automatically calibrate a 100-qubit processor over the weekend. So the ingredients for the 3 parts I've already shown to you. C1 we do with GOAT, programs in TensorFlow. C2 we calibrate, for example, using ad hoc closed loop calibration with the black box model. And for C3, we can use machine learning techniques, or we can simply essentially use GOAT that now has a Hamiltonian that depends on a set of parameters beta. And instead of optimizing our pulse parameters alpha by gradient descent as we're used to, depend a cost function G that also depends on beta, freeze the pulse parameters, and then adjust the beta parameters to also minimize the model deviation. So here we're going again back to optimizing the model. So in principle, this whole game of fixing the model is simply not fixing the Hamiltonian and finding the pulse parameters, but finding the pulse parameters and fixing the Hamiltonian. So here are a few results from first runs. I'm showing you data from last winter because tomorrow Federico and Max will show you when you're also refreshed and you have let this settle some newer data. So this typically shows you a convergence plot over various calibration runs. So this is a closed loop calibration, a C2 step, and you see the black scatter in fidelity between 0 and 1. Actually, this should be 1 minus fidelity on the left side because it goes lower with more iterations, fidelity becomes better. So you see that depending on how you do your randomized benchmarking, you have a fairly bit scatter, but it goes lower, and that around 25 to 30 iterations, you're getting a fairly good fidelity. Here is an example of model learning. We are taking a single qubit, and we are also assuming that we have a single two-level system. So one of these material-based pieces of dirt, and we try to figure out the right model and with it the right fidelity. So the first thing you see that the fidelity here converges quite quickly after about 5 iterations. You see that on the upper right, we have taken around a parameterization of the line response function. So V is what you send in and omega is what's coming out, and this is given in Fourier space. We have a control signal that has a carrier envelope form, and we have some fidelity. And you see that while we are running this optimization over a couple of iterations, we are taking our initial guesses for the unharmonicity, delta sub omega, and for all the other parameters of the experiment, like the coupling to the two-state system, the frequency to the two-state system, and everything else to a good value fairly quickly. You can also see that some of these values are changing while the fidelity is already fixed. The fidelity stops at 5, and you see that, for example, GTLS, even after about 10 iterations, still is changing, which automatically tells us that these parameters are not really important for controlling the fidelity. They're important for knowing the model, but the fidelity doesn't depend a lot on them, which means we have just learned something about the sensitivity of fidelity to this very specific model parameter. So we do learn something from this model identification. So the good news here is that this works. It gives us the parameters fairly quickly. It also tells us what parameters are important. We really need to figure out delta sub omega, the upper line in the inset, and we need to figure out omega q, the qubit transition frequency, the lower line in the inset. But the rest is fairly straightforward. The really bad news is the y-axis of the f of beta plot, which essentially tells us that we're converging, but the result is not really good. And now we are enriching the model. So we are essentially doing, human machine learning. So we're taking the C3 step and we're putting in a new thing into the model by hand. You see that this is an older version. It didn't do it automatically yet. And we see we're essentially putting in that there's also a T1 and a T2 decoherence time. And you see, we now need we need more iterations to converge, because now specifically the T1 decoherence time, shown in the middle inset, really needs to be adjusted well, but then we converge much better. So this model little example told us that T1 and T2 are really important, otherwise we get bad convergence. So this way we have pulled out important model information, and we have validated that the basic idea works. And here is the red line, which is with the TLS, with the coherent noise source, but not with the incoherent noise source. And you see it was totally worth it to include T1 and T2. So you can wonder, now we are running this big robotic machine, and I think a number of the PhD students working on this were doing some very high-level coding of things that look like they're simply software development. And indeed, you may wonder, where's the physics? Well, the physics you have just seen in the last plots, it's in the model. So basically, everything that C3 puts around it is laboratory routine, is essentially this fully handed over to AI. So we are optimizing, so we are taking out a lot of routine work out of calibrating an experiment. And it's very similar in a way that optimal control, traditional optimal control replaces the experimenter's intuition and coming out, say, with the right Rabi pulse and discovering the right pulse shape. We are now, on top of this, also taking out some of the human intuition in essentially finding out the precise model. But of course, physicists now need to find out what families of models are reasonable. So the level of kind of sophistication of what to think about has just been increased. Some type of routine work in the lab is now put out by more exploratory work, and this is very typical for any type of automatization. So this is we plan to extend this with more transfer functions, quantum jumps, and more open systems features, with confusion in the measurement, so modeling correctly state preparation and measurement errors, crosstalk, so you drive one qubit, but you really also hit the other, and things like that. And we now also, of course, want to go into a way that the artificial intelligence can suggest the best possible experiment. This is called Bayesian experimental design. It's in principle a well-known technique around artificial intelligence. However, it's quite hard to really get working right at an acceptable time. So this is not done yet. So the main mission of QuSCo, which is to really find pulse sequences that give you the best output of your sensor, in this case, the model learning, is not yet achieved with the current version of C3, but you see that we are on the way of that. Now, let me show you one final thought. So all these closed loop methods that are optimizing the parameters of gates in a quantum algorithm is what we're used to. So we are optimizing the blue boxes on the upper panel that are part of the algorithm. But modern variational algorithms actually also on the outside, so between the beginning and the end of an algorithm, are variational problems. So I think one direction we should think about connecting to these near-term quantum processors is to essentially do also a bit more optimal control, not on a single gate, but on a full algorithm level, where there's a whole set of new challenges. This just as an outlook. Now, this is already the outlook. Tomorrow, Federico will show you a much more detailed and sophisticated example of C3. And we will see an early application from Max Werninghaus that shows you how you can actually get very close to the quantum speed limit. And I've already mentioned that the short-term goal for us is to find a good model. And you see that we are always capitalizing good model because we consider this to be a fixed technical term and for complex chip, but we would also like to broaden the base because ultimately, even though the motivations I've been giving you were all coming from superconducting qubits, where the fabrication tolerances are probably currently quite pressing, it seems that this will happen in other platforms also at some point. When we are densely packing ND centers, so the interaction between them depends on model parameters, there will be an uncertainty. In optical systems involving traps, the traps' degree of freedom play a role. It's not as big as in superconducting qubits, but ultimately they play a role. So the method that we have designed to applying optimal control to superconducting qubits have challenges, and we think that the method we have will allow to overcome them. I think I've talked slightly too fast. That gives us more time to questions, and nobody objects for the last talk not running over time. So thank you very much for your attention.
Okay, so thank you very much, Frank, for this very interesting talk. So giving so a beautiful overview of the field. So is there any question? So in the chat? No, not for the moment. So I have so one question. So maybe it's a naive question. So would it be possible to realize that I could call a closed loop optimization process, but in real time? So I mean, that you correct so the model system, so at the same time where we apply the control field, because for the moment, so the different processes
Yeah, so I think you should still see my slides. So this type of tune-up essentially runs a pulse sequence,
Mm.
collects data, and while collecting data, updates the pulse sequence. So it's not real time in the sense that it happens during a quantum coherent experiment,
Yes.
but it happens kind of within a couple of T1s. I
Okay.
think with everything else, we are limited by simply computing power. Running these more sophisticated model searches takes a while. And if we were to try what you suggest, we would do two things. We would use a system with a very, very long T1
Mm.
and with a generally low time constant. So we would look into atomic physics and we would try to do something simple. We haven't
Okay.
benchmarked how many orders of magnitude we are away from this yet.
Okay. Okay.
But of course, one option is to take something very simple and instead of running in TensorFlow, hard coding it onto a field programmable gate array. But we haven't tried this out yet. You know, we are very happy to be where we are right now.
Mm. Okay. Okay. No, I understand. So any other question about this talk?
I realize I have gone fast, and I have
Yes.
not seen your facial expressions. Usually, when I see
Yeah, sure,
facial
sure.
expressions, I slow down and only get through half of my talk. But in the online world,
Yes.
this is not really possible.
Yes.
And I'll actually look at you by looking at an empty screen because my camera is
Yeah,
on
sure,
something.
sure. I can add my yes.
Yeah. Okay.
Yes. No, no, because so my feeling is that in robotics, for instance, in a
Hmm.
real-time closed-loop experiment, so you don't need exactly the detail of of a model system, for instance, and only a partial information about the model system and real-time experiment measurement
Yeah.
allow in
I think
general to converge to. So maybe it's
I think I have kind of one remark is so we are not there yet, but
mm,
then of course the time constant in these experiments are
yeah,
nanoseconds, which they are
sure,
not
sure.
in robotics.
Yes, sure.
And also we have to look at questions: how much resolution do we want to reach?
Mm,
And this is certainly something to explore in future, but it's not something we have optimized for yet. I
sure,
mean, I
sure.
think the early claim to fame was to take a calibration procedure from half a day to 10 minutes,
Mm,
and we take it from there.
sure,
Maybe
sure.
Max, I don't know whether Max is on the line that he can comment on how long this typically takes, but so far it also hasn't been, so far the procedure is also not hands off yet. So,
Mm.
or maybe Max can comment on this tomorrow.
Okay. And when you said that so I don't remember exactly, in 1 week or in few days, so you can optimize so the control pulse. So it's really a black box experiment at the end.
No, we go back and forth between white and black box.
Okay.
So we basically, after the initial calibration, we are improving our white box, our
Mm,
model, in order to make the black box tune up faster, to get much closer.
okay.
So we're not getting stuck in local minima, and that we don't have to do so long, because this is typically the time
Mm,
limiting step. Whatever you want to do with a model, you want to do with a model.
sure, sure. Okay. Yes, I think it depends a lot on the information that you have about the model and yes.
Yeah, yes. And as mentioned, we have discovered with IBM Zurich, so I'm probably now taking away Max's punchline, that they could make pulses very fast. And we know that for having a high Rabi frequency, you need large power. And at some point, the input line couldn't handle this anymore. And this was a very, very unexpected error source.
Mm,
And I think this is a level of discovery we can make currently here.
okay.
Because we have essentially, I mean, I think this is very typical of a lot of people experience with quantum optimal control, which is you're beating some known issues, some known limitations of your system, which means in the experiment, you're discovering the next limitation. And we are trying to take this human process and automatize it as much as possible.
Mm. Okay. So I think so there is no other question. So maybe we can stop there. So Mattia.
Well, thank you very much for everyone. Thank you, Frank, for your talk. Let me stop the recording.